We were doing this ballistic vehicle tracking example of an extended Kalman filter. We talked about this in the previous video. Here was the physics, the model we're talking about, the true physics of the situation, we assume. It's a continuous time nonlinear case, okay? And you'll notice here, there's no noise. The only thing noisy is the measurement. There's no noise on the process. But when I put it in a state space format, I added this thing, which is process noise. Why would I add process noise to my Kalman filter model when it wasn't in the physical model? So that's what I want to talk about now and the results of this Kalman filter, of this particular example. We went through how to come up with the resulting extended Kalman filter. Here's the equations. Either we would calculate or a computer would calculate. And what happened next was simulating this. We simulated truth so that it was like true truth. It followed those physics precisely with no process noise. And I'm going to say we added this to the model so that we could tune our filter. Even though there wasn't real process noise in the real original continuous time equation, we're kind of accepting that we added a lot of errors going through all our approximations to linearize and discretize. There was a whole bunch of approximations. So there are errors that are unaccounted for, and we want some way to deal with that. And we deal with that by adding this guy on. Here's how our Q matrix is computed. We had a way to compute all this. This is now our tuning parameter. We set it to 0. We're saying Q equals 0. We need 0 process noise. We don't like Q to be 0. We needed to cover our sins. So let's see kind of what happened. First, let me explain these charts. Solid line is our error in our estimate of altitude. Difference between our estimate of altitude and the simulated true altitude. These dashed lines are the square root of the P11 term of our covariance matrix. What is that? It's an estimate. It's how accurate the filter thinks it is. It might not be how accurate the filter actually is. It's how accurate it thinks it is. And in our case, the P11 term corresponded to altitude itself, the x1 state vector. So the square root of that thing is just the standard deviation. So these two limits kind of are plus and minus 1 standard deviation. We would expect our error to be within those limits approximately 68% of the time, 2/3 of the time. And this was a case where we did just set that tuning parameter to 0. Measurement error was 1,000 feet. And things look kind of like they might be okay. The error is mostly within these limits. Maybe it's close to 2/3 of the time. And the filter keeps thinking, or thinks that it keeps getting more and more accurate. Since the Q matrix is going to be 0, it's going to keep shrinking down to 0. It's going to end up thinking it's perfect. What if we take everything the same and make the actual measurement error much more accurate? From 1,000 feet to 25 feet. You'd think everything would get better, right? Well, it starts out kind of looking normal. Then, whoa, off to Never Never Land. Filtered divergence. You're not only outside of your confidence limits, you go way off. Why does that happen? Remember, we linearized everything about our current estimate. Once your estimate starts getting off, your linearization errors get off. You kind of get this self-perpetuating bad feedback thing happening. So what if we take this same situation, but now we'll put in something other than 0 for sigma sub u? We'll say it was 10. Now look at a couple different things. One is the filter doesn't think it's going to get perfect. It seems to kind of flatten out, doesn't keep shrinking. The confidence interval doesn't keep shrinking to 0. The other thing, the error stays mostly within those limits, and it looks, I think it actually did turn out, it was very close to the 68% of the time that you expect to be within plus or minus 1 sigma. The other good thing is it looks like it's above 0 about as much as it's below 0. So you have an unbiased estimate. We like unbiased estimates. And we like our filter to have an also accurate estimate of its uncertainty. So this looks like the filter's estimate of its own accuracy actually reflects its actual accuracy. All good things. So here's a comparison where the only difference was what we set that tuning parameter to. In this case, the filter thinks it's getting more and more accurate when it's getting more and more inaccurate. It finally goes outside the filter's uncertainty bounds, stays outside, and goes even further outside. We call that, we call that filter divergence. In this case, the filter, its uncertainty bounds reached a kind of limit. You know, it didn't just keep going down forever. They reflect the two errors roughly. About 2/3 of the time, you're between plus and minus 1 sigma, and the bias looked to be about 0. All good things. Before I totally end this video, let me talk about the P matrix. This is what P means. It's kind of hard to understand. What it ultimately is the filter's estimate of how accurate it is. Along the main diagonal of P are the variances of your state variables, or its estimate of the error variance of your state variables. And all these little rows are the correlation coefficients. So your P matrix of the Kalman filter is keeping track of all its estimated error variances of all the state variables and their cross variances. It's a total statement of how accurate the filter thinks it is. That's how we, calculated these dashed lines from the filter itself. So that's a little morality tale about these tuning parameters. And by the way, I think you come up with these by trial and error. They're not derived from the basic physics of things. You have to probably simulate things. Why we came up with 10, there was probably some trial and error that said 10 seems to work about right. 0 was no good, 10 looked pretty good. Anyway, that's that story about tuning parameters and that injecting noise into your model. You're not actually injecting noise into your estimator. You're just trying to account for all the uncertainties that came about because of all the approximations. Anywho, that's it for this video.